Okay, so our next presentation is about, as you can see, Dockerizing Microservices. Our speakers are Diogo Monteiro and Raffi Der Haroutiounian. Is that correct?
Yeah.
Oh, thank you. Okay, I'll just give you a little bio about Diogo. Diogo is a software engineer working on CD.OS, a cloud management platform focusing on software-defined infrastructure workflows by creating a single pane of glass where cloud operations can connect to public and private cloud providers, such as OpenStack, CloudStack, AWS, and Docker, and manage their environments through a unified REST API providing portability and flexibility. Diogo is also involved in the research of different techniques and tools that can be utilized to improve development agility. Techniques from the Lean Startup methodology and tools like Jira, Git, Jenkins, and Docker are utilized on a daily basis, which allows for small iterations to be performed on each individual microservice, which is then delivered through a CI/CD pipeline. Data from the feedback loop of building, measuring, and learning is then evaluated, which helps narrow the focus and improve the product development lifecycle. On this spare time, he researches. Now, Raffi is an adaptable full-stack engineer whose current responsibilities include working to improve and develop the front-end UI and UX of CD.OS using JavaScript, AngularJS, and Node.js, while also adding functionality to the back-end API and database using Java and MySQL. He works with OpenStack, CloudStack, Docker, and Amazon Web Services to normalize their feature sets to a common, easy-to-use UI and set of APIs. Most recently, he has been working on a new service catalog platform with the intent to provide a solution to the complications of deploying complex applications on various cloud providers. In his spare time, Raffi experiments with new and upcoming technologies to better understand them and determine if they may be useful. His side projects have led him to study more about Docker and the usefulness of centralization in both development and production scenarios. Please welcome Diogo and Raffi.
Thank you. So thanks for coming to our talk. Now that you know my whole life story, we can start talking about Dockerizing microservices. Diogo and I are both recent graduates from the BSD program here at Seneca. I see some familiar faces, some not, so hello. Today, we're going to be talking about, well, the presentation is split up into two sections. The first part is about the fundamentals and a little bit of an overview of what Docker is and containers. We'll talk about monolithic versus microservice architectures, the types of virtualization that's available to us, the history of containers, Docker, what it is, why we would use it. We'll talk briefly about Cloud Dynamics CDOS, which is our current product that we're working on. And I'll briefly mention the 12-factor app, which I'll detail in a few minutes. Second half is going to be more about the actual act of Dockerizing your application. So we'll talk about preparing for Dockerizing your application, what Docker images are, the complexities of them, optimizing those images, the ins and outs of Docker networking, the Docker pipeline for continuous integration and continuous deployment, and then finally some tips on running Docker in production. So to get started, because we're not sure about the depth of skill sets in the audience, I just wanted to briefly make sure we're all on the same page about virtualization and cloud computing. So when we say virtualization, we're referring to the creation of a virtual machine that acts like it's a real computer. It increases the productivity of your hardware because instead of running one application on each box, you're running potentially hundreds of them. It's used extensively in organizations and even institutions like Seneca. Cloud computing is a little bit of it builds on top of virtualization. We hear a lot about cloud. What is cloud? It's just a thing in the sky. But it's really just a layer on top of virtualization that enables on-demand access to a shared pool of resources. And it's primarily used to enable developers and operations to focus on delivering a product rather than having to deal with infrastructure complexities and owning your own hardware. So to understand what Dockerizing microservices even means, we first have to understand what the terms monolithic and microservice architectures even mean. Monolithic application structures refer to one cohesive unit of code that's sharing the memory space and resources, and all the different components are working together in a fairly tightly coupled manner. An example of this would be an ASP.NET Web Forms application where the server delivers the UI, and then you have all the business logic tied in with the application. There's not a lot of separation of purposes. The benefits of monolithic applications are that the different components, it's really easy for them to communicate with each other. If billing needs access to user data, it's right there, and vice versa. And potentially, it could perform better because shared memory access is a lot more efficient than inter-process communication, though it's a bit of a debatable topic at this point. The downsides of monolithic applications is that because it's so easy for those components to talk to each other, it becomes tightly coupled. So there's no reason for the user component of the application to have references to billing or vice versa. But in often cases, because it's there, we end up coding it in that way. And that can make it difficult to scale because if one component of your application is only getting hit one time per session access, meanwhile your billing is being hit multiple times a second because it's counting all your resources that you're using. Which one would you rather scale? You don't want to scale both of them at the same time. It's a waste of resources. But with monolithic applications, you get either all of them or none of them. With microservice applications, you have a lot of smaller independent applications that have their own memory space and potentially even running on completely separate machines. The benefits of that is that you have improved application organization. So in a lot of cases, you have a service that just does one job. If you have a proper microservice hierarchy, then you'll have that service doing one job. You know that it does that job, and subsequently, you can scale that application independently of all the other ones. So you can make better use of all your hardware resources because now you don't have to scale all of these things and all that extra overhead along with it. That thing that only gets hit one time per session, leave it there. It's only going to get hit one time. Billing or whatever other resource you have, just scale it up and it will make better use of your hardware. The downsides of the microservice architecture are not really a downfall of the architecture itself. It's more that when you migrate from a monolithic application, you end up with potentially having cross-relating components reveal themselves that you didn't know you had before, and that can increase the scope of actually getting that migration done on time and correctly. And potentially you could end up with a very messy code base because if you go a little bit too ahead of yourself and you end up with hundreds of services, then it's not any better than a monolithic application at that point. You don't know where anything is. I want to talk briefly about three types of virtualization: hardware, platform, and operating system. Hardware virtualization is basically a virtual machine. If you run VirtualBox on your machine running Windows or Linux, you're running a virtual machine. You give it a dedicated set of resources, like CPU, memory, disk, and that guest OS thinks it's running on dedicated hardware. It has no idea it's being virtualized. And that's really good for running legacy software because sometimes it's not worth the effort of bringing old software over to new modern operating systems. Platform level virtualization is done on it's also known as application level virtualization because it allows developers to focus on their software and not how to deploy it or the hardware it needs to run on. It abstracts away all the hardware and you say, I want to deploy my application, do whatever it takes to make it happen. Sure. There's examples of that like OpenShift and Bitnami. If you're not familiar, you could just go kind of one click and you have WordPress or any application that you want to deploy and it's just up and running. You don't have to worry about networking and all these things. Operating system level virtualization is container-based, and the rest of this presentation is kind of based off of this type of virtualization. Each container shares a single kernel, which makes it really efficient on hardware resources because you don't get the overhead of every single application you want to launch having its own set of resources that comes along as dependencies for no reason. You already have it, so it just uses it. Before we get too much into containers and Docker, a brief history of containers and how we even got here in the first place. Way back in 1982, way back I guess, Linux came with a feature called chroot, or chroot, which changed the apparent root directory of the current process you're in and its child processes, and effectively made the rest of the file system hidden. That modified environment is called a chroot jail, and if you're a Seneca student, you're probably experiencing something similar to this when you log into Matrix, where your user account is your root, and you can't really leave that area because that's the area that you've been given access to.
Because 1982 there wasn't a
That's a good point. The next point, I think this was more on. I don't have the answer to you actually. That's a good point, because the next slide actually refers to BSD jails, which is the next iteration on top of that, which partitioned the system into several independent mini-systems called jails. And that was different from chroot in that it actually sandboxed the jailed processes so that now actually it is isolated, whereas on chroot it's not truly isolated, it's just the rest of the file system was hidden from you. And that served three purposes: virtualization, security, and ease of delegation. And ease of delegation in the sense that because the jails had limited scope, you could give access to a process to say you have access to this jail and not worry about it somehow gaining super user access to the rest of the system. But I'll try to follow up with you on that one. Following that came Solaris zones, which just another iteration which had zones that acted like isolated virtual servers. But the point I'm trying to make here with the history is that we saw that fairly early on, they tried to solve this container-based virtualization methodology. And slowly, especially near the 2000s, we started to see a more of an increase in actual focus on developing these kinds of tools on the Linux kernel. And so two developers from Google ended up creating Linux control groups, and on top of that, namespace isolation, which are kernel level features. So C groups, for example, isolate the system resources of a collection of processes and limits them and prioritizes the hardware, like the CPU, the disk, the memory, the network. And then the namespace isolation will take those separate groups of processes and make sure that they can't see other resources that are running in other groups. So those two Linux kernel features are then utilized by Docker by way of LXC. And LXC is just an acronym for Linux containers. The LXC combines both those tools to provide an isolated environment for applications, and you can view LXC kind of like an in-between between chroot and a full VM, because you get almost a full Linux kernel installation, but without the need for that kernel on each container. It shares one kernel for all of them. So now we're at Docker. This was around in 2013, Docker was released. Just as a show of hands, how many of you know about Docker? Okay, that's good. How many of you have actually used Docker? Okay, just about right. And how many of you have actually deployed Docker in production? We got one. That's one more than I expected. Okay, so that's good. Now we all know why we're here then. So for those of you who didn't raise your hand about knowing about Docker, Docker is an open source project that basically takes it automates the deployment of applications inside software containers. So it provides an additional layer on top of that operating system level of virtualization. And the result of that is very, very lightweight containers because of two particular features, union file system and copy on write. Diogo is going to go a little bit more in depth on the union file system and copy on write, but just on a high level, a union file system is a file system that amalgamates all a collection of different file systems into one logical file system. And it does so by building layers of file systems on top of each other with just enough libraries and binaries that it needs to run your application, no more. And each container that has similar layers shares them until the point where copy on write kicks in, where you need to make a change to one of those layers. It will make a copy of it locally, and then you kind of treat that as a new layer. But until that point, it shares them. So when you have 30 containers, but they are all based on Ubuntu Linux, you don't get 30 copies of Ubuntu Linux. It shares all of those kernels together. So why containers as opposed to just sticking with virtual machines and platform virtualization? Hardware virtualization is limited on one end in that virtual machines are not designed to share hardware, share hardware resources rather. So when you give it 1 gig of RAM, it takes 1 gig of RAM and it's not going to give that back until you shut it down, whether the application inside needs it or not or ends up utilizing it. And the hypervisor itself consumes about 10 to 15% of your machine resources. So you're really giving a lot away just to run a virtual machine, and you're getting way too much overhead. On the other side of the limitation spectrum, you have platform virtualization, which is too simplistic for a lot of complicated applications, especially microservices, because at that point, it's really easy to deploy, okay, I want WordPress, but beyond that, it gets complicated and very hazy when you want to do inter-component communication. Operating system level virtualization maximizes tenancy and performance, and that's because you will take all the unused resources and reallocate it to those who need it. So then why Docker specifically as opposed to just using Linux containers? Docker has a unique feature in that you can encode the development and deployment practices directly into the image like a blueprint. And that's handy for developers because then I could use the same image for development as I do in production. And then I can focus on what I actually want to do, which is develop, as opposed to operations and infrastructure, which me and Diogo know way too much about operations and infrastructure because of this. For operations, it actually simplifies the deployment process because all the dependencies are baked in. You just have to deploy the image. And at that point, you can also argue that there's no more, well, it worked on my machine, and then the developer walks away kind of thing. If it worked on the developer's machine, it will work on the production because the environment the application is running in is the same. But the most important feature is probably that you have sub-second start time. So Docker images are ephemeral, and Diogo is going to go into what that means later, but basically it means the image is stateless. The container is stateless. So you could start up and stop Docker containers, no problem. So for operations, if there's a component of the application that's messing up, you just take it off, put another one in. Within half a second, no one even knew that you brought a service down and back up. It's really good for trying to assuming there's no bugs in your code, you can get the production back up and running if something hits a wall. So to briefly talk about CDOS or CDOS, depending on your inclination. At Cloud Dynamics, we're developing a cloud management platform called CDOS, which basically is designed to simplify public and private cloud platforms into one unified platform. So you have OpenStack, CloudStack, Docker, AWS, and a couple of more down the pipe. It allows you to build, deploy, monitor, and manage your cloud environments through a single source, which would be CDOS. And in addition to that, it provides a full unified REST API. So if you're a developer who wants to talk to AWS and OpenStack, but you don't want to have multiple paths of code just to talk to different providers, this API would allow you to deal with all those complicated mappings because we've already done it for you. We've also added on user management with two-factor authentication, billing and usage reports, service catalogs, which are basically one-click deployment of applications, and theme management and white labeling. So if you want to be a reseller and give this as a solution to your clients, there's also that capability. The reason why I'm mentioning this product is because we too had a monolithic application structure where it was just one blob of code, and it would crash, and if it crashed, the whole thing would go down, and then it would take time to get a new patch up and running, transmit the build to the server, get it up and running. The downtimes were horrendous. It just wasn't working. And that's why we even started on this endeavor for microservices, because now we ended up with something more like this, which each individual job has a service, and if it has problems, it may go down. We may fix it or update it or work on it, but the rest of the application stands alone. And it makes things easier to update as well. So we could iteratively develop on top of things while it's on production, because we could just take one single component, bring a new one in, and there's no downtime. It also makes it easier to work with other developers without stepping on each other's toes, because if I'm working on one component and someone else is working on another, we don't have merge conflicts, or I don't have to pull his changes before I commit. It makes things a lot easier. So the final thing I want to mention is the 12-factor app, which is a methodology for building modern cloud applications. I'm not going to go into too many details here. If you want more information, the URL is right there, 12factor.net. But basically, if you're developing a cloud application, you should be following these principles. And the one we found particularly useful was the third factor, which was configuration. We used to use JSON config files, where depending on if we were on development, QA, or production, we would tweak a string, and then it would do different things for debug mode and whatnot. When we went to Docker images, because those images are immutable, which means they can't be changed, the configuration had to be injected through environment variables, which is exactly what the 12-factor app suggests. And if you have the environment-specific changes, you should do it on the environment variables, because then that way your code is the same no matter where it's deployed, and just if there has to be some variations, it's done on the environment variable level. Just a tip in case you wanted to go live with one. So at this point, I want to pass it off to Diogo, who will talk about actually Dockerizing your application.
Okay, hello. Right, thank you, Raffi. Okay, so it comes time to Dockerize your application. A couple of concepts that's it's important to understand. First of all, like Raffi mentioned before, the container should be ephemeral, meaning that they should be transient. So the application shouldn't store data on the container itself. It should store the data on a database, for example. So if the end user is connecting to your application in a cluster mode, you should be able to remove a container, add a new one, and that shouldn't impact the end user. The next point, which is crucial, is that a container is the same as a process. So if you look at the Docker host where all the containers are run, you will see that each container has an individual process. And that brings to the other point, which the container should only have one process in the foreground. That's not a technical limitation, but more of a community preference. And that tying back to the monolithic versus microservice architecture. If you keep multiple processes in a single container, you're adding complexity. So it's harder to maintain, and it becomes really bad. So you really want to separate that. I can give an example. When we were porting CDOS to run on Docker, the billing service was handling both an HTTP interface and had the schedule built in. So then it came a time we had to scale horizontally the billing service. So by consequence, the schedule got scaled as well. But the schedule wasn't built in to run in a cluster mode. So then we had some problems. So if you follow the principle and you keep one single service running in a single container, you can avoid those complications. If, however, that's not a possibility for you, you have the application, you can't modify it, then there are some workarounds. So the first workaround, you can use a supervisor, which in the foreground inside the container, and then spawns multiple daemons in the background. The next option is first just use LXC. You get the same benefits as Docker because it runs on containers, but then you don't have the one process limitation. You get a full OS to play with. So what about Docker images? So images are the basis for containers. So Raffi mentioned a bit before about layers. So Docker uses the union file system, which is a combination of files and folders, which they call branches. Each branch can have a read or a read-write permission. So Docker has a variety of storage backend providers. It works with the AUFS, the RTFS, OverlayFS, ZFS, you name it. So each storage driver has a different use case. So when you deploy Docker in production, you could try to achieve more density. So then you choose a different driver, or you want more performance. There's a really good talk about that from Jerome. He's a Docker developer, and then we're going to link on the presentation notes later on. So the image itself is the basis that you can run the container. But then how do you create an image? You need a Docker file. So a Docker file is just a set of instructions. So even before talking about the instructions, one point I want to make is that you can think about the image layers the same way you think about Git. So with Git, you track in your application source code. With image layers, you're going to be tracking the application install steps. So this is the same concept. So the Docker file instructions. So there are a bunch of instructions you can use on your Docker file. We're going to be covering just the 4 more important ones. So starting is the from. So every Docker file needs to have a from instruction on the top, which mainly refers which base image to use. So if you know object-oriented programming, you can have a base class, and then you're going to extend that base class, which consequently you're going to inherit all the properties. So that's the same concept here. You're just inheriting a set of instructions from the base image. Next instruction is the run. So run, you can execute some commands to build your image. So you can do an apt-get, yum install, curl, whatever you need to do to build your application. Then you have copy, which allows you to copy your application source code to inside the image. And then finally you have the command. The command defines the entry point for your application. And that ties back to running one process on the foreground per container. So in the beginning, when we're just first porting the microservices to run on Docker, we just grab all the install scripts that were for VMs, and we just dump in a Docker file, build the image, and then we're trying to run the microservice. And then the container would start and exit right away. And then after scratching our heads and trying to debug, we realized that because the VM install scripts were running the application as a daemon in the background, which is the way you want to do it if you run in your application in a virtual machine, because you can't just lock the foreground. But in Docker, it's the contrary. You want to run the application in the foreground. If not, the container won't be in an active mode. Final piece is the image cache. So that's a very neat feature from Docker. So when you build the image from the Docker file, what happens is Docker looks at the from base image, creates a new container, which gives you a read-write image layer. Then it executes the follow instruction inside the container, and then commits that into a new image, and then keeps doing that until it doesn't have any more instructions in the Docker file. So that allows you to cache all the instructions you have in your Docker file. So this image right here, kind of like you can visualize what's happening in the background. So you have all the storage drivers as the bottom layer, and then you have a base image, and then one instruction to add Emacs. And then you commit that, you have another instruction to add Apache. And then later when you run the container, it's just a collection of images with a read-write permission. So how about creating efficient images? The first step you want to take is you want to chain commands. So what you don't want to do is have multiple run instructions. So let's say you're going to install Node.js. So you first install wget, you download the Node artifacts, you untar it, and then you move it around, create some links, and then you have Node. However, that is creating an image layer for each instruction. And then once that layer is committed, you cannot remove the files that were committing to that. So you're going to end up with your image with wget and the Linux, the Node.js artifacts, which are not crucial to run your application, and just going to increase the final size of the image. So if you're going to be pushing that image over the wire, you want to reduce the size as much as you can, because then you're going to introduce some time penalties. So what you do want to do you want to combine and chain all the commands into a single instruction. So first you install wget, download the Node.js artifacts, untar it, and then you remove the artifacts. And then you go about, you move it, you link it, and then you want to install wget. So then you're going to reduce the final size of your image. The other approach you can take is the top to bottom. So that means you're going to use the cache when it makes sense. So what you don't want to do is to copy first your application source code and then put at the bottom an apt-get update. So that's it's going to take a while. It's going to download some system packages from the internet. And then next time you modify your application source code, then you copy, and then you do a new build, it's going to invalidate the apt-get update cache. So it's just going to take more time to build it. What you do want to do is first run the apt-get or any other system instructions that you can cache, and then you copy your application source code. So when the cache is invalidated by modifying the source code, you can still reuse the cache of the apt-get, which is the previous layer. But even better, you can run your apt-get, cache that, and then you copy the files that never changes. It's a file that you know is going to be there and you're not constantly modifying when you develop. And then you copy a file that changes sometimes. And then you copy the files that always changes. So this way, Docker can better utilize the cache and offer better times for your build. So how did we created the base images for all the microservices we run the Cloud Dynamics? So initially, we were using the Ubuntu image, but later we switched to Debian because it's a bit smaller, about like 100 megabytes. It might not sound much, but like I said, when you're pushing and pulling, you want to make sure you have the smallest image as possible. Then we authored a Java runtime image, which we configure Maven, we modify some environment variables. We have a Node.js runtime as well. We author an image like that, and then we have a Golang image. With Golang, I'm not sure if there are any Golang developers in the room, but the community views package management in a very peculiar way. So when you build a Golang application, you actually all the dependencies are statically linked. Even the runtime itself is statically linked. So theoretically, what you could do, you could have a very tiny Docker image, like a 2 megabyte image. You can use BusyBox, and then you can just run your Golang application there. But that's a topic for another time. So about the image building process. First thing you don't want to do is deploy images straight from the internet to your environment. You do want to keep track of all the dependencies of your applications in an internal repo. That means you first analyze the dependencies, download them, and then you provide to our developers in an internal repository. Most of the public repositories for a variety of languages, they do not run on HTTPS. Like it's very easy for somebody to exploit you with a man-in-the-middle attack. You want to avoid that. The second bit is you want to create a process to author the base images and then make them available to developers. So the goal is to avoid black boxes. So if anybody here is familiar with big data applications under the Apache umbrella, like Kafka, Zookeeper, Storm, that to install them, you need like a team of people. Like it's not just like a single one-liner script. And usually in that process of installing it, you got to download a library that a dude compiled somewhere, and then that's pulling some dependencies from another place that you have no idea. So you end up with this big black box, and you have no idea to verify that all the dependencies inside that black box are actually good, like they could be exploited. And the final bit is you want to think about failure scenarios. So imagine you deploy hundreds, if not thousands, of containers to production, and then a new Java zero-day exploit pops in. How can you update all these containers in a timely fashion manner? You don't want to take days. You want to take minutes, hours. So if you have that hygiene process, you can easily push patches to your environments. But then leaving all the technical bits aside, what's the secret sauce about Docker? Like why an open source project that has about 2 years old, it's so big and got so much popularity? So in my view, the first part, if anybody here ever had to deal with Linux containers, that to share the root file system of the container, like it's a pain. Like there's no easy way. And with Docker, they created this concept of a Docker image, which is not a new technology. It's using like Linux proven technologies. But then it gives you the option to create a human readable tag and then share that image via an image repository. So Docker made really easy to use and made the process sociable. So if there's only like one thing you take from this presentation, is that if you make your project easy to use and you make it sociable, like you have the recipe for success. Okay, so all that sounds good, and I hope by now we're able to convey why would you use Docker, but without networking, all the containers would be useless. So here is just like an overview of the default network mode that Docker comes in with. So initially you have your host physical interface, the ET0 right there, and then Docker create a Docker0 virtual bridge, and then from that bridge, when you create containers, it creates a pair of VIFs. One VIF, which is a virtual interface inside the container, and another pair in the Docker0 bridge. So this way, the containers can communicate with each other and also reach the host network. Then you might be thinking, okay, the containers can communicate, they can go out, but how do I get access to the containers? So Docker has this concept of exposing ports inside the container. So then you can tell Docker which application, which port your application is going to be listening to inside the container. And then you can tell Docker to publish a port on the host. So what it's doing is doing a port mapping. So then you could have the application like web server inside the container listen on port 80. And then you can publish the port 88 on the host. So behind the scenes, what Docker is doing is writing an IP tables forward rule, to forward the traffic from the host interface to the container VIF. So the way I see all this, because coming from a developer, so take with a grain of salt, like networking is hard. To be honest, I don't know if anybody like it besides networking people, no offense. But I see Docker creating network as a service. So like it's wrapping all the complexity and then just giving developers an easy way to manage infrastructure without having to know about all the infrastructure details. So how about running simple containers? So initially, let's assume here on the side, taking like one of the CDOS services, it's an application container, and then you have a database container. So they both get an IP on the same network. But then following the 12-factor app principles, you're not going to be hard coding the IP of the database into your application. You're going to be using a domain name. So then the application tries to resolve the database domain name, but then it can't find an IP. So then this model is broken. So how the question is, how do you link applications? So Docker has a native solution for the inter-container communication problem. So using the same example, you have your application container, but then this time you tell Docker to link to the database container. So then Docker goes and associates the database domain name with the database container IP. So now the application can resolve the database domain and thus connect to it. But, okay, so under the hood, what's happening? So Docker creates a etc host file. If anybody's familiar with Linux, which I believe people are since this is an open source conference, on the, on the Linux OS, you have the etc host file, which you have a list of IP addresses and domains. So Docker creates one for each container, and then mounts that etc host inside the container. So then by the time you link the container with another container, Docker updates the etc hosts with the container IP and with the domain name you specify. So in the case that the link container is restarted, Docker would assign a new IP address. So then because it's mounting the etc host file inside the container, it has a way to go and update dynamically. Besides managing all the domains when you link containers, Docker also does some IP table management in the back. So Docker has a flag to disable inter-container communication, which it could be useful if you have a self-serve cloud environment. You don't want to have a flat network where like all the containers can talk to everybody. So you can disable that. If you do, by enabling links, Docker creates a IP table rules to allow communication only between the linked containers. Okay. But linking is not all the best. There are some limitations. So first limitation does not support bidirectional communication channels. So in a microservice application, you're going to find out more often than not that you have services communicating in a bidirectional way. So if you just have a database, the application is going to communicate to the database, but the database does not need to communicate with the application. But in a microservice architecture, that's not the case. That's why probably you guys are going to see that star diagram being referenced when talking about microservices. It's like in a monolithic way, you have like nice layers and arrows only going in one direction. But in microservices, you have like hundreds of services and everything's communicating with everything. Okay, so about linking. Besides the bidirectional problem, and another issue is that if you recreate the container, so let's say in your development workflow, you're going to make code changes to your application, you're going to rebuild the image, and then you're going to relaunch the container. Any existing links to that container are going to be destroyed. So then you're going to have to recreate pretty much your whole application, which adds some overhead and it's not ideal. Another reason why links shouldn't be used across the board is that you want to have a layer in between your services. It could be a proxy, or it could be a load balancer. You don't want to have hard links between all your services. So then, if you don't use links, how can you offer service discovery for your applications? So that's where DNS doc comes into play. So first of all, why DNS? So DNS, like you guys saw, Docker uses DNS in form of links in a way. And then DNS is also a proven technology. A lot of people are familiar with. Pretty much every network stack of operating systems supports DNS. So it makes sense to just reuse DNS instead of reinventing the wheel when dealing with service discovery. And then what is DNS doc? So DNS doc is a DNS server implemented in Golang. So Golang is the same language that Docker has been written with. So DNS doc, it hooks to the Docker event bus. So then every time a container is created, DNS doc is aware because it's listening to all the Docker events. And then looks at the container IP and then adds an entry on its own internal server with that container IP and a name you can specify. DNS doc also provides a REST HTTP interface to manage all the names, and it's driven by environment variables. So you can say it's cloud aware. Another very important point, and one of the reasons why we chose to use DNS doc was, well, when you have a new technology, it's never the case you're going to migrate all your environment at once. Usually you're going to take baby steps. It's going to be like an iterative approach. So you migrate first the non-critical pieces, and then slowly when the team gets more familiar, the technology matures, you're going to migrate the mission-critical pieces. So with DNS doc, because it has an HTTP interface, you can add domain entries for services running in virtual machines, in other networks, in bare metal servers. It doesn't care, it's platform agnostic. So it's a good benefit. And just to make a point about DNS, you guys probably heard about OpenStack today. And just on the latest release, the OpenStack Library released, they introduced a concept of DNS as a service. So up to this day, which I believe OpenStack's 3 or 4 years old, they didn't have DNS as a service. But you can see that's the direction they're going. So the whole industry is kind of trying to use DNS as the tool of choice to handle service discovery. So here you can see just a basic topology of how our Docker host looked like. So you have all the application containers, and you can see they all have an IP address. So by the time they're created, automatically DNS doc adds an entry with their IP and the domain name we want to resolve to. And then in this case, we have a virtual machine running a database, and then manually we can add that IP and that domain to the DNS doc server, which then enables all the containers to resolve the database domain name to the correct IP address. Okay, so what about orchestrating containers? In a monolithic application, you just have one script, you run it, your application is up, you don't got to worry about. But then if you have multiple microservices, you got to somehow have a way to start them at the correct order and define settings in a proper way. So mainly when you look at the orchestration, you want to have a blueprint to run your microservice application. So the native solution that Docker offers, it's called Docker Compose. So it first started with a project called Fig, which later Docker Inc. Was called .cloud before. It acquired Fig and then incorporated that into the Docker ecosystem and named Docker Compose. So Docker Compose, it's mainly consists of one YAML configuration file, which you can define all the relationship of your services. and then define settings for those services. And then with one script, you can run, and then have the microservice application up and running in your Docker host. However, orchestration is still an open market for tools. There isn't one de facto tool that everybody uses. So if you look around, some tools you might be interested would be Maestro, Shipyard, Crane, Clocker, Bosch. Bosch, it's a good one. Rancher Compose as well. Swarm, which is also part of the Docker ecosystem. Okay, so now you have all the pieces. How do you integrate Docker into your existing pipeline? So at Cloud Dynamics, we already had a Jenkins pipeline built. So when we decided to integrate Docker into that, we didn't want to disrupt the existing build pipeline, because some of the clients, they were relying on the artifacts we're producing to run our application in a virtual machine. So we just created separate Jenkins jobs for each new microservice we were introducing. We decided to use the Cloud Beast plugin. It's a very nimble Docker plugin for Jenkins that offers all the functionality you're going to need. And then we had a pool of Docker build servers, which we would use to build the images for all the microservices. And then finally, we decided to use Docker Hub, which is the SaaS registry that Docker offers. Pretty much is an image repository. So the flow in an overview, what would look like is first, each microservice job would pull the code from Bitbucket, and then would build the image for that service. And then if the build was successful, we'd push the new image to Docker Hub. And then for QA environments, we would automatically orchestrate the deployment of the new builds using Docker Compose. So what about incorporating Docker into the development workflow? Because that's important as well. Because if you're going to move to use Docker, you got to make sure developers can still operate and use Docker on a daily basis. So for Linux, runs natively since it relies on some Linux kernel features. For Windows, on the latest version, I believe they just introduced support for running Docker natively as well, using the Hyper-V. So it has a different view of isolating each process, but then it just provides the same API interface. So then Docker doesn't care. As long as the underlying system has that functionality, Docker can work with. So if you are running a Mac, which Cloud Dynamics, pretty much everybody runs a Mac, we had to use Docker Machine. So Docker Machine is the tool that Docker created and offered for Mac developers to run Docker into a Mac environment. So what it does, it creates a Linux virtual machine, and on that virtual machine is very tiny. It's about 24 megabytes, and then it runs a Docker daemon, and then also installs a Docker client on the Mac. So then you can access Docker transparently. Also, it does other things like sharing the folders from your Mac with the VM. So then this way, you can build images and mount volumes, and it's all transparently to you. But however, if you're looking for better performance, you might want to check out Vagrant Boxes. Not getting a lot of details, but if you use NFS, share with Vagrant Boxes, you might gain a little bit of performance when sharing your folders with the Linux VM running Docker. Okay, so what about running Docker in production? As we saw, I think there's one person in the room that actually deploy Docker to production. At Cloud Dynamics, we haven't deployed to a production client yet. We have it running in our QA environment and our development environment, but we're planning to get Docker up and running production soon. So a couple of points to think about before going into production. First, you want to think about container monitoring. So you're going to have hundreds or thousands of containers. How do you monitor and make sure the containers are performing the way you expect? Second is log management. The containers are going to be generating logs. How are you going to aggregate that and visualize it? And finally, a multi-host deployment. How do you make sure containers running in multiple hosts have a seamless management plane to your tools? So some tools that people are creating to run Docker in production are Rancher, Kubernetes, and Cloud Foundry. Rancher, it's a tool being developed by the Cloud Stack founders, as well as some developers from Sun. Kubernetes, it's being developed by Google. It's known as the X Borg project. And then you have Cloud Foundry, which is being developed by Pivotal. So they're all open source projects. You can go to the websites. You can check out some demos. We personally have been following Rancher more for like about a year. We know the team, and we've been using their platform in our local environments, and we believe like in a few years that's going to be the platform that's going to kind of like have a control on the Docker production deployment. So I encourage you guys to check it out. So that's pretty much it. If you guys want to find more about us, you can tweet us at the Cloud Dynamics handle, and we're going to be posting the presentation notes there after the fact. So thank you. If you guys have any questions, please.
Any questions? No?
So I have a question actually. So the thing is, the way that I understood this is that you've shifted the complexity, or at least Docker has shifted the complexity from development to orchestration and production level. So essentially, what I don't get from this is, let's say when we had the VM scenario, yes, there was a lot of wastage, but then we knew exactly at production time that this is what the limits of the hardware were. When it comes to Docker containers, I really did not get the exactly the orchestration parts of it. Deployment is fine, but then when it's running, how do we actually? Maybe that's because that was out of the scope of your presentation. The other question that I had was, let's take the situation where you were saying about Vietnamese. I don't know what the name of
OpenShift?
Yeah, where you have WordPress. So I don't see how Docker solves that problem exactly, because it's still a slice. And for example, let's say when you take Vietnam, you had to install MySQL, you had to install PHP, and there was a little bit of ugliness that could be present in that case. But I don't see how Docker solves that. Yes, Docker does do some excellent work in DC host and OpenDNS.
Okay, so I think your first question you can split like into parts. So the first is about resource utilization. So with a VM, like Raffi covered, you have the hypervisor, which is just already consuming 15% of the hardware available. So with Docker, you can still imply some constraints using C groups. So you can't tell a container can only use 4 gigs of RAM, or like it can only use 2 cores available in the host. So you still have a way to manage the resources, but you don't have the overhead of running on a hypervisor. As far as the orchestration, it's still a new field. People are creating tools, but the same way you have problems orchestrating the deployment of virtual machines, and like how you're going to orchestrate the applications running inside the virtual machines, that that problem translates as well to Docker. But then if you look at the community, people are focusing on trying to solve that problem using Docker, and the virtual machine is already becoming a legacy technology. Then I guess on the Vietnam piece.
Yeah, with the point with the OpenShift and Vietnami was more the fact that with the linking of containers using DNS doc or just straight up linking, you can solve a lot of those. You could still have the separation of purpose of each container, and then they can talk to each other. Whereas on platform as a service providers, they tend to focus on just one application. You want WordPress, so that container is going to be spun up with both WordPress, like Apache, and MySQL in one. They don't really spin up 2 containers and link them. So that level that's fine for WordPress, but when you get beyond to more complicated applications like ours, where we have maybe up to 20 services that need to talk to each other, with platform as a service, I don't really know of a way to accomplish that. If you have one, let me know. That make sense?
Yeah.
I had a question how you guys at Cloud Dynamics actually solved your log management issues with so many Docker services running.
Yeah, so right now we're still working on that. We're looking at options like Logstash, and then we have Logly too, and syslogs and other tools. So we're still playing around some options, and then we're going to decide which one we're going to adopt.
Highly suggest Logstash.
Logstash, yeah, we hear a lot of good things. Yeah.
Yeah, we've been looking a lot into that recently.
The question, I was listening to your answer to the previous question, and near the end you were talking about
well, if you're spinning up WordPress and you've got to have a MySQL and stuff like that. I don't really understand the moving parts completely at the base. Are you saying that you have several different things that would share the same MySQL, or your WordPress and your whatever the hell would have their own copies of MySQL?
Well, like in our scenario, at least currently, we have multiple services talking to one database. But it's kind of up to you to actually isolate that. We may eventually end up at a point where each service, because it's a separation of purpose, you'd have its own database.
Because if you were sharing the database, then why didn't you just run regular Unix processes and forget all this virtualization and so on?
Yeah.
Virtualization containers and so on.
So when you say like a Linux
It
process,
sounds like you're going around in a circle here.
You don't have the DevOps.
I think just to get back to the question, like with the Linux process, like Docker itself, it's a Linux process. So it's more like you're not changing the underlying technology, you're just introducing a tool to make development and operations easier. And then by doing that, like you're gaining performance, and then like we're able to utilize hardware better. But in a sense, yes, you have like a database, container. And then if you look at domain-driven, like patterns, like yes, like theoretically, you want to have a complete, separate domain. So then each service would have its own database. It could be running the same physical MySQL server, or it could be spun across different clusters. But the idea is just like introducing tools to help the process be easier.
Another question, if it's okay. When you have a packet going in the system, does it pop up in userland multiple times? Is the virtual switch in userland, or is it all in kernel space? That's a performance question, actually.
Okay, so the underlying, way that Docker uses networking, I won't be able to answer specifically, but what I can say is that each container does not run with privilege mode. So it does not have, admin privileges to the host that's actually run the containers.
Yeah.
But yes, as far as performance, that part I'll have to go back to.
It's just, if you watch a packet traveling from the real network into your container, I'm just wondering if it ends up popping up to a process in userland that does this virtualization of the switch.
And here, Docker uses virtual bridges. So user uses bridges and also VIFs to enable the container intercommunication.
Right.
As far as the flow of the packets and the performance, that part I'm not really sure about it.
Thank you.